Thank you for your interest in my poster entitled Challenges of Assessing Number-Based Particle Concentration and the Development of a Quantitative Method Using DCS. This piece of work was a collaboration between the National Physical Laboratory and Oxonics Therapeutics. More information about their proprietary Sonotran platform can be found here on the poster. Number-based particle concentration is an important attribute of industrial particle formulations. It can be used to assess product batch-to-batch variability and as a measure of dosage for therapeutic and medical applications. Unfortunately, measurement accuracy and precision remain a challenge to industry due to the lack of relevant reference materials and standards. Here I describe the development of a method to measure number-based particle concentration using differential centrifugal sedimentation, or DCS. DCS is a high-resolution technique with excellent repeatability. The graph on the right shows good repeatability between different batches of Sonotran particles. The insert shows an even better repeatability using aliquots of the same batch. This technique can't, however, make a direct measurement of number concentration. We measured different dilutions of batch 1 to build a calibration curve shown on the left. The number concentration was measured directly by particle tracking analysis, or PTA, and the mass concentration was measured indirectly by DCS. We came up with a conversion factor between DCS mass concentration and number concentration. We put this conversion factor to the test using a fresh aliquot of batch 1 and 2 additional batches, batches 2 and 3. The number concentration measured by DCS using the calibration curve was in agreement with the number concentration measured directly by PTA for all 3 batches. This is shown on the graph on the right. The method with the DCS also showed lower variability than the direct PTA measurements. To conclude, we have demonstrated using a real-world industrial product that we can use a calibrated DCS approach to measure number-based particle concentration. The DCS approach exhibited lower measurement variability than PTA and can potentially be used as a tool to evaluate batch-to-batch variability and support the development of products with enhanced safety and performance profiles. This work was made possible by the UK Department of Business, Energy and Industrial Strategy.
Greetings, let me introduce myself. I'm Volodymyr Tutko, a PhD student in the University of Bayreuth, working on the layered silicate nanocomposites. So while they are interesting, first, they are more or less naturally abundant, they have a high aspect ratio and nanosheets geometry. And when they're immersed into water, they swell automatically, delaminating toward the single nanosheets. But with natural clays, you need to have a high input force in order to strip the single layer from the crystal. And with our synthetic clays, you actually don't need any force. You can just move them into water and they will eliminate till the single nanosheet. This is the figure 1 and figure 2. In addition, our sodium heptaride possesses astonishingly high aspect ratio, 20,000, and the cost of single sheet is just 1 nanometer, which makes them perfect for the barrier properties and mechanical properties, coatings and polymers. But the osmotic swelling were limited previously only to water-based systems, so which limits us from using a lot of polymers, including hydrophobic, and we had to go to the solvent plants where we have found that the mixture of acetonitrile water methanol, acetonitrile water ethylene glycol, and glycerol carbonate water acetonitrile allow us to reduce the water content to a few percent. It's a blend with polymers which were previously not soluble in pure water, so expanded the range of constant parameters. But for a lot of applications, we actually don't want to have water, so that's why we found another way of triggering the osmotic swelling is by adding the crown ethers to the solution of highly polar solvents, which triggers the ideal osmotic swelling, and we get the gels which can be further processed as nanocomposites or with the hydrophobic polymers or water sensitive functional groups as isocyanides, and also be used in the battery applications where even traces of water cannot be tolerated. Let's see figure 3 and figure 4. Thank you for your attention. If you have any questions, please ask.
Good morning, everyone. I'd like to present you some work that we've done at Imerys on dispersing kaolin for printing inks. So basically, the issue is kaolin is a hydrophilic aluminosilicate, so it likes to be dispersed in water, but sometimes we want to be able to use it in oven-based applications, and one of them is heat-set inks for glossy magazines. And we need to make sure that the kaolin doesn't change the printing gloss. So we've got various options. Obviously, at Imerys, we're doing the right processing so that we're reducing the amount of large aggregates in the kaolin by doing the milling. But what we need to look at as well is really when the kaolin particles are included here in the ink varnish, that they're going to disperse as well as possible back to their single particle size, and there are no agglomerates formed. That would guarantee that when the kaolin is added to the ink layer, that you don't get any large particles sticking on the top, because that would reduce the gloss, which is not what we want. So to look at dispersion, we've known from previous work that we can use primary amines. They work quite well. But this paper was very interesting. It also looked at more bulky amine to give extra steric stability. And the interest as well is there a very simple dispersion test where we can use kaolin, which has high density, so wood sediment, and put that in solution and directly the ink distillate. And what we find here is some comparison of different surface treatments. So here, for example, you get directly very quickly very large agglomerates form, so we can see that this is not acceptable. Whereas you can see that the second and third treatment look better, sediments more slowly. And if we increase the dosage of that treatment, we can see that it sediments very, very slowly. It's just a few particles here. And then basically that allows us some optimization. And the other interest is to look once the kaolin is fully sedimented, because if there's issue of flocculation, if there's not enough steric repulsion, then you'll have large flocks. So there'll be a distance between each particles. And there is an example here of a very large flocky structure. So with this very quick test, we can decide which surface treatment looks the best. And we've basically put the treated clay back into the ink and then done some printing tests, and we can see that we got very glossy surface. And here's an example of a very smooth layer with no kaolin sticking out of the surface. But gloss and technical is not the only thing we need to look at. We need to consider the health and safety of the treatment, also the viscosity, because we're spraying it on the kaolin, and basically optimize the cost. And for that, we're looking at optimization and maybe looking at some blends. Thank you for your attention, and I'll be happy to answer any questions. Thank you.
Great, thank you very much for those three posters. I guess everybody should hopefully be unmuted who's the speakers. Any particular questions, anybody? If you want to unmute yourself and ask one, there's an opportunity now. Otherwise, I will pick up any questions that are in the chat. Great. Okay. Right. Beth. Good morning. Good afternoon. No, good morning. Yeah.
Morning.
Just trying to remember where everybody is. I don't know. I was just thinking. I mean, number-based particle sizing is interesting because I mean, I can understand how it can be very important for quality control, but is it almost too sensitive? I mean, my logic being that 1 nanometer, well, 1 10 nanometer particle is actually 100,000 or a millionth of the volume mass of a micron particle. So if you really are looking at numbers, then sometimes you could be, reacting to something that may not have an impact on the product performance. But that's what I was just trying to understand, is the sensitivity there.
Yeah, so I think it depends on what you're wanting to do with your product. Obviously, some products, the very, very small particles might not have much impact on the product performance. In other formulations, that's going to be completely different. But I think this really taps into a really core question in formulation science, which is, how do you represent your data? Do you want to look at the number-based distribution or the volume-based distribution? And this is something that I think we all probably encounter on a regular basis, and making sure that you're using the right distribution and converting between the two correctly, if that's something you do, making sure that's done correctly is really important.
Yeah, I mean, I can understand that a small number of particles of small size, which would show up in a number distribution, could have significant safety implications, for example, I guess, which could be quite interesting. I mean, we managed to get a patent once where we stated that it had to have a number of particles below a certain size. And all that meant is you just had to get the measurement better and better, and you could always find them. So, yeah, but not a very good example, but yeah, I mean, I can see from a safety point of view, but it's just interesting. No, thank you. A fascinating area, and yeah, something that I think people don't necessarily think about enough. Asking for a single point measurement, what's your particle size, obviously doesn't mean very much. Asking what's your particle size distribution doesn't mean very much unless you, actually, do you want surface area volume numbers? So thank you, that was useful to bring out. Thank you. Great, okay. Any other questions? Otherwise, Dudko, you're there, all right? Assuming I pronounced your name correctly. Thank you, Beth. Dudko? Phil, can you see Dudko on the list, and is he unmuted? Let's have a look.
He should be able to unmute himself. Let me just have a double check for him.
See if he's...
He's there. Let's ask him to unmute himself.
Yep. Hello.
Hi, Dudko. Sorry. Great. Good. Thank you very much for your presentation. That's interesting. I mean, in your title, you talk about perfect nanosheets. Do you mean literally single sheets?
Yeah, they are literally single sheets.
And in these systems, you're able to stabilize them well enough to be used in products?
Oh, the more interesting that they are actually stabilizing themselves because they are negatively charged. And it's actually even quite hard to, like, whenever you reach a certain threshold in volume percent, they're just stable almost infinitely. And mostly we were able to incorporate them into foams and nanocomposites together with the polymers by solution blending. Yep.
Okay, no, interesting. And I mean, once you go into an organic solvent, that charge stabilization won't be effective, I guess.
The charge on particles itself is quite high, but yeah, the volume content for the stabilization of the liquid crystal is changing. Yep.
Oh, interesting, challenging. Yes, thank you. Okay, thank you very much. Annabelle, good morning.
Good morning, Simon.
Hi. Thanks very much for your talk on kaolin in printing inks. I mean, printing inks, the processes being used for printing are continuously changing. is that creating new challenges for your inks, for your kaolin to go into inks?
It depends, obviously, of the printing technology. Indeed, there's still the old technology offset, which is very much used. So it's still very valid, and this is what this work was based on, and that changes the way the kaolin and also the pigments. The pigments are obviously very difficult to disperse. So there are some well-known technology for these, like bead milling and triple roll mill that is used for that. But obviously, you're right. There are new technologies, and the digital printing area is a bit more tricky for us to access. And indeed, for this one, we need to potentially look at new ways of dispersion. Because, for example, photocopy printing, we're not using that technology at the moment. But obviously, pigments are used, so some of the dispersion knowledge is obviously very useful for the technologies.
Great. Okay. Yeah, thank you. Okay. And you've answered a question around ammonium, quaternary ammonium compounds.
Yeah, obviously, because quaternary ammonium are well known for making nanoclays, and they are used quite a lot. But part of this work was also to propose something without quaternary amine because of patents. Sometimes, in the industry, we have patents that we need to look at other technologies, and we find that other amines actually work really well from literature and from some of our work we've done in the past and confirmed here. So it's nice to know and to understand the technology. I'm not presenting everything here, but there are various techniques to sort of check how the amine attached to the clay, like Hammett indicator, and that's really useful to understand that we're putting the right amount, the right treatment.
Okay, great. Thank you very much, Annabelle. Thank you very much to Beth and Dubco too.